All right, so the last thing I want to define for you before we think about the purification, which is in a sense going in the reverse direction, is I mentioned last time when we did the example, the partial trace of the maximally entangled states turned out to be the maximally mixed state, right? Very famous example in quantum information and quantum mechanics. And we had the notion of maximal there, so maximally entangled, also maximally mixed. What does that mean? Before we just defined entangled versus separable, so it was a binary thing. It was either entangled or it was separable. But there are notions that you can define the amount of entanglement that let us make statements, for example, that this is a maximally entangled state. And that also comes from the Schmidt decomposition. So we say that the number of non-zero lambda I, the number of non-zero Schmidt coefficients, is the Schmidt rank, or Schmidt number, of the state, the bipartite state, psi A, B. And this will let you quantify the amount of entanglement. So remember, the singular values, which are exactly the Schmidt coefficients, are always going to be non-negative, but they can be 0. And so the more non-zero Schmidt coefficients that you have, the more entangled the state is going to be. Higher Schmidt number is more entangled. Lower Schmidt number is less entangled. If the Schmidt number is 1, there's only one non-zero lambda I in this expression. Then you can see that it corresponds exactly to our notation of separable from before, right? Why is that? If there's only one non-zero lambda I here, then the summation goes away. And I have something on A tensor something on B. That's what we define as a separable state, right? So this Schmidt decomposition recaptures that, but it gives us a more general expression. The higher the number of non-zero singular values Schmidt coefficients are, the more entangled the state is. And we capture that in a metric known as the Schmidt number. That's what we'll use for now. You can also define this as an entropy type quantity. So lambda I is being non-zero and the square is summing to 1. You can think of that as a probability distribution. So there's notions that we'll get to later once we do entropy, where we can think of this as the entropy of entanglement. So you also see that as a metric to define the amount of entanglement. But for now, just the number of non-zero lambda I is the Schmidt number.